Hey physics students, Campbell here. In our third video on optics, we're going to talk about refraction. Refraction is what happens when light enters a transparent medium of different density. We're going to talk about Snell's law, we're going to talk about the law of reflection and total internal reflection. All right, now this is part of geometric optics, which is the study of light rays, Newton's big thing. And what Newton said is that light travels in a straight line. And from this little picture here, you can see that, right? We have a ray of light coming in and it's hitting this piece of glass. Now, part of that becomes reflected. Right? So we get reflection. We talked about that with thin film interference. I get some reflected, but I also get some transmitted into the medium. And because it slows down when it enters the medium, it actually bends a little, and that's called refraction. In fact, it bends in the case of going into a denser medium. We see that it bends toward the normal line. What's a normal line? We'll talk more about that in just a sec. Also, we do get some absorption of the light ray. Remember that light is the oscillation of electric and magnetic fields. So when it enters a medium, it starts oscillating the electrons in the atoms. And so that results in some absorption. So not all of my light is reflected when I have a transparent medium. Not all of it is refracted and then will come back out of the medium, but some of them actually gets absorbed. Now, first we're going to talk about this reflection here. There's a law, and it's called the law of reflection. And what it says is that the angle at which the incident ray hits the surface to the normal line has to equal the angle of reflection of the light ray to the normal line. So the angle of incidence equals the angle of reflection. So now, remember I said the normal line? Well, a normal line, remember, is perpendicular to a surface. So my normal line here is this line here, which is at where the light ray hits the medium. And I draw it just perpendicular to the surface. So this angle here has to be the same as this angle here. Now, remember I talked about the fact that light waves slow down when they move into a denser medium? Right? They have to move those atoms. So it slows them down. And remember I said frequency doesn't change? Remember? Frequency doesn't change. What doesn't change? Frequency doesn't change. And if velocity is equal to frequency times wavelength, if frequency doesn't change, then the wavelength must change. So here I have light coming maybe from air into, I don't know, water. And we can see that water's denser than air, right? So we get smaller wavelengths. But because it slows down, what happens also is I get a bending of the light. So here's my light wave. It hits here, and then as a ray, now it's bent. And remember, refractive index is the speed of light to the speed of the medium. So if I have a denser medium, my wave's going to move slower. Now, how much does it bend? Well, that's actually called Snell's law. So here I have light traveling from air into water, and if I measure the angle to the normal line, here's my incident angle, and as it travels in, it bends toward the normal line when it gets into water or glass or something more dense, and here is my second angle. Well, how do I figure out what that second angle is? Well, that's called Snell's law, and what Snell's law says is that N1, or the refractive index of medium 1, times the angle, the sine of the angle of incidence, theta 1, is equal to the refractive index of the medium it moves into times the sine of that angle. And again, these are all measured to the normal line. Now, what this means, if you think about this, is that if the refractive index increases, so I move into a denser medium, the ray bends toward normal. So that ray of light is towards the normal. But if I move into a lesser dense medium, right, the ray speeds up and it actually bends away from the normal. So in fact, if we kind of flip this, if I shine light in the water, like maybe I have a light bulb in water, right, the ray would travel up this way. So this would be my incident angle, and this would be the angle of the light in the air. So it bends away from normal. So one way you can tell if a medium is got a higher refractive index than the one it came from or a lower is to look at the angle. Now, beautiful thing about Snell's law, we can use it with our velocities for lambda equation. We could use it with our refractive index equation. We can put them all together. And I say that there's many forms of Snell's law, not just n1 sine of theta 1 equals n2 sine of theta 2, but I can set up ratios of stuff. So, and notice here that sine theta 1 over sine theta 2 is also equal to the ratio of velocity 1 to velocity 2, which is also equal to the ratio of lambda 1 to lambda 2. Notice they're all 1s over 2s except for here, right, with the refractive index, and that makes sense based off Snell's law equation. So all of these are 1 over 2 except for refractive index. Now this is really helpful because if you know wavelengths and you know one of the angles, you can calculate the other without having to use refractive index. Pretty cool. I have a question for you. I have light traveling into glass, and when it hits glass, it's traveling at 60 degrees originally. When it hits the glass, it bends to a new angle of 34.5 degrees. In water, it bends to 40.6 degrees. Which has a higher refractive index? Well, the denser it is, the more it slows down. The more it slows down, the more it bends. So if you said glass has a higher refractive index, you are correct. In fact, glass is like 1.5-ish, and water's about 1.33. All right, let's do a practice problem. So I have a light ray traveling through air, and the refractive index of air, which you need to know, is 1, because we're going to round. It's incident on water, which has a refractive index of about 1.33. Part of the beam, of course, is reflected, and its reflected angle here is 60 degrees. The other part of the beam is refracted as it travels through our denser medium, and I want to know what is theta 2. Well, Snell's law, right, is n1 times sine of theta 1 equals n2 times sine of theta 2. Well, first of all, we have to figure out what is n1. Well, by the law of reflection, right, n1 is 60 degrees, right? Law of reflection says the incoming angle has to equal the outcoming angle measured to the normal line. So now I just got to set up this equation. Now, there should be a 1 here, right, because that's just air. But so I have sine of 60 is equal to 1.33 times the sine of the angle I'm trying to find. So do some math. You get 40.6 degrees. Much less, right? Because I'm moving into a denser medium. Now, just one little thing, if you're ever on Survivor and you need to spearfish for, food so you can survive, Survivor, the fish that you're seeing is actually deeper than what your eyes see. Because remember that, so here's a chest, a treasure chest, and it's down at the bottom of some body of water, ocean, lake, whatever. And here it is down below here, and the light rays come off of it, right? They hit the surface of the water, and they bend away from normal. Now, only the light rays that enter your eyeballs are the ones that you see. So what your eye interprets, your eye is not smart enough to know what the angle of refraction is for any specific medium. So your eyes interpret light as traveling in a straight line. So instead of seeing the bending and the chest where it is actually at the bottom, your eyes interpret as a straight line. And so if we draw the straight line back, that's actually where your eye sees the chest at, or the fish. But it's not really there, it's actually deeper. And we actually have a name for that. It's called the apparent depth, because apparently that's where your eyes think it is, but it's actually deeper. So deeper and closer to you if you want to spear that fish. All right, let's talk about another topic called total internal reflection. Now, if you think about being underwater, like if you have gone snorkeling, right? If you're under the water and you look up, straight up, right, you see the stuff above you, like the clouds in the sky. But as you start to look sideways, so as you look sideways to a point where you see nothing, it's kind of like blurry, and then everything else you see is a reflection of the stuff in the water with you, so the fish or the rocks or whatever it is that you're snorkeling around. So this happens because the water that you're in has a higher refractive index than where you're looking. So remember that when light travels from a higher refractive index to a lower refractive index, it bends away from normal. So as we look to the side, right, that refraction angle increases, and at some point the angle of incidence to the angle of refraction gives an angle of refraction of 90 degrees. This is when you don't see anything. It's like real blurry at that point. Everything else after that angle, you get total internal reflection. So you can see the stuff that's in the water with you. It's so cool. Now, the angle at which the incident angle at which the refracted angle, not the reflected arrow, but the ray, the refracted ray is 90 degrees. That's called the critical angle. And then everything greater than that critical angle will be reflected totally internally, like the turtle. You can see the turtle and the reflection of the turtle in the water once you've reached greater than the critical angle. So let's think about this. So for our critical angle of incidence, our angle of refraction has to be 90 degrees. And this only happens when the refractive index outside is less than the refractive index of where you're viewing or where that light source is coming from. Now, if we set up Snell's law, right, we would have that our refractive index of water times the sine of that critical angle, the angle at which all of it just stops refracting or reflecting, that's equal to the refractive index of air times the sine of theta of air. So if we solve this, rearrange it, right, the refractive index of air is 1, sine of 90 would be 1, divided by the refractive index of water, which is 1.33, I will find out that the critical angle for water with a refractive index of 1.33 is 48.8 degrees. So as soon as I turn my head so that the light rays going from my eyeballs to the surface, it makes an angle to the surface of 48.8 degrees to the normal, then everything's going to be fuzzy. And then I get to 48.9, suddenly I see a reflection of all the stuff that's in the water with me. So there actually is a formula for the critical angle, although you just get it from Snell's law. So the critical angle is the arc sine of the ratio of n2 to n1. And remember, n2 has to be less than n1. Refraction is 90 degrees. Now, one thing that's really cool because of this whole bending phenomena, if you think about light shining through a prism, right, it spreads out the colors. And this is because each wavelength of light actually has a different refractive index, so it bends differently. In fact, as the wavelength of light increases, the bending or refractive index decreases. And that's why if we shine light through a prism, we actually will see the light break out because they all have different amounts of bending or refraction or refractive index. And we'll see that we get the red light on top and the blue light on the bottom because it bends more. Pretty cool. So remember that wavelength increases, refractive index decreases, or the light bends more. So that's an inverse relationship. This is also true for rainbows, right? If you look at a rainbow, right, light travels through all the air droplets that are left after the rain. Some of it totally internally reflects. And so some of this, so the light gets spread out into its different colors because each light wave or wavelength bends differently. And in fact, when you look at a rainbow, what you see is the blue is actually on the bottom and the red is coming from the top. And that's just because blue bends more. And each droplet, right, only the light you see is the light that actually enters your eyeballs. And so the blue looks like it's on the bottom. So if we look at a rainbow, blue is on the bottom. And if you're great, you get a double rainbow, which is totally cool. That's another reflection back. You'll see that the wavelength or the rainbow pattern is actually reversed in the second rainbow. By the way, can you tell where I took this picture? All right, fill out your WSQ. I've got a couple questions for you. Here's the first one. Pause the video, see if you can answer this. And here's my second one. This one's a toughie. Which one is the right possible path of the light ray through this prism? All right, I'll see you in class.